Okay, our second speaker of the day is Hector Salgado, who will talk about numbers that cannot be written as the difference of harmonic numbers.
So again, I'm Hector Salgado. I'm a little sick, so if you could excuse me at some points. But again, as you'll notice, that the only difference in our titles is she has can and I have cannot. So you'll see a lot of similarities down the road. So starting off, this was joint work with Natalia and Serbin, and we were funded through the Pump Undergraduate Research Grant and the NSF grant. Okay, and so jumping into it again, the definition of harmonic numbers. So a harmonic number is a number that can be written as a power of 2 times a power of 3. Or it looks like this, right? So some of the examples, if you start plugging in A's and B's independently, you can get 1, 2, 3, 4, 6, 8, 9. Okay. So then the reason that we started looking into these numbers is because we saw a presentation by Lenstra. And he talked about Dimitri, and he talked about Gersonides, and he talked about the ABC conjecture. And as we heard before, Dimitri was the one that found the consecutive pairs of harmonic numbers, the octave, the perfect fifth, the perfect fourth, and the major second. And then Gersonides, he wrote up a proof, and this was 675 years ago. I can't stress that enough, right? Because it just tells you how long people have been looking at these numbers, right? And it says the only two consecutive harmonic numbers greater than 4 are 8 and 9. So again, you look at 1, 2, 2, 3, 3, 4, and then greater than 4, you only have 8 and 9. Okay? And then again, this is a table of harmonic numbers less than 1,000. So right across the top, you have the powers of 3 less than 1,000. Across the side, you have the powers of 2 less than 1,000. And then you just treat this like a regular multiplication chart. The 2 times the 3, you get 6. 2 times the 9. And keep going. Okay? Okay. And then we looked, we naturally, again, looked at the differences between these numbers. We knew that we could write 1, 2, 3, 4, 8, 9. So we looked at more numbers. And we found the numbers below 100, there's 11 of them, and these are the 11, 41, 43, 59, and so on. Correct. And then now we're going to define an NDH number, which is just the numbers that can't be written as a difference of harmonic numbers. Okay? So numbers that can be written as a difference of harmonic numbers look like this. Take this one, right? Power of 2 times the power of 3 minus the power of 2 times the power of 3. Okay? And right now we're going to look at the number 41. And this is a proposition. The number 41 is not is an NDH number, so it cannot be written as a difference of harmonic numbers. And it's a proof by contradiction, but we have two cases, right? Again, if you look at the generic form, right? You have a 2 and a 3 here and a 2 and a 3 here, but you know that 2 doesn't divide 41 and 3 doesn't divide 41. So both of these terms cannot have 3 and a 2, so they have to be different. So first we take a look at case 1. So in case 1, we have 2 to the a minus 3 to the d is equal to 41. We move the 3 to the other side and write it as 2 plus 1. Then we use our binomial expansion, and we take this 1 and this 41, we add them together, and then we divide out that 2. Okay? And then once we get here, we have this side is even, so we need this whole side to be even, and everything back here all has a factor of 2. So we need this to come out to an even, so d must be odd. Okay? And then, so we work with d being odd. So working with d being odd, we do the same moves, right? Except this time we write it as 4 minus 1. And when we're writing it as 4 minus 1, we have to keep take into consideration that it'll have alternating signs. So when we write it out this way, we get a minus 1 at the end, and then we can combine it with this 41, and we get a 40. And then we can divide out a 4. And then we get an even is equal to an even, but in order for this side to be even, we need this to be even. And since before we had d is odd, and now we have d is even, it's a contradiction. Okay? And that takes out the first case. So now we go into case 2. And in case 2, we have a power of 3 minus a power of 2. And we do the same moves. Same moves again. Move the 2 over, change the 3 to a 2 plus 1. And then we expand it out. Get rid of the 1s here. Right? And then we have an even over here, so we need an even over here after we divide out a 20. I mean a 2. Right? We get this even, and we need an even, so b is even. And this one gets a little bit more complicated than the previous one. The previous example was fairly easy. but this time we need b equals 2k. So we set b equal to 2k because it was even, and we're supposing k is even to start off with, and we write it as 2l. So substituting it in, we get b is equal to 4l, or 3b is equal to 3 to the 4l, which is also the same as 81 to the l, right? And if you multiply 81s again and again and again, you'll notice that the last digit is a 1. So when we're here, right, this 81 is congruent to, 81 to the L is congruent to 1 mod 10. It just means that this term is always going to end in a 1. But we know here that 2 to the C plus 41 never ends in a 1. Because if you have this ending in 1, that means that this has to end in a 0, this 2 to the C. If that 2 to the C can't end in a 0, because then it means it has a factor of 5. And we know that 5 does not divide 2 to the C. So this implies that k is odd. So after all this, we get the k is odd. And we work with k is odd. So we do it again. We let k equal 2l plus 1. We sub it in and we get 4l plus 2. And we put it as the exponent of 3. Right? And then when we look at powers of 3, they have a cycle of 4. And their digits, the last digit kind of repeats. And this one ends in 9. Okay? And in order for this one to end in 9, we need 2 to the C plus 41 to end in 9. And then in order for 2 to the C plus 41 to end in 9, we need 2 to the C to end in 8. Okay? So once we get here, this tells us that C is odd. Because again, when you take powers of 2, you're going to see that they cycle. And every other odd generates an 8 at the end. Every other odd power. And so we work with that again. And now we know that C is odd. And so now we write this 2 as a 3 minus 1. Because we know C is odd, we know how these signs alternate, and we know that it's going to end over here in a negative 1 when we do our binomial expansion. And then I distribute the negative across, right? I move, oh, it didn't change it. I move this positive 1 to the other side, and then you see this whole side, and you see that it always has a factor of 3. And then you have a 40 here, right? So you factor out a 3, and this right here, this 3 times this whole thing, right, is equal to 40. It implies that 3 divides 40, and it doesn't. And since 3 doesn't divide 40, we get a contradiction, and I could have sworn I changed that. It's the same thing. But this implies that 3 divides 40, which is a contradiction. And so 41 can't be written as a difference of harmonic numbers, but 41 did come up in a couple of other interesting areas. So it is the largest of Euler's lucky numbers. And if you look at Bach, you know, J.S. Bach, right, the famous composer, in a lot of his works, he uses the number 41 discretely, or the number 82. If you look at his works, it'll cut off at 41 measures, or it'll cut off at 82 measures. And 82 is also another number that can't be written as a difference of harmonic numbers. Another thing is if you look at a natural order alphabet where A is 1 and Z ends up being 24, but this is because you count I and J as the number 9, U and V as the number 20, you end up with Z at 24. But if you take this natural order alphabet and you look at its letters, so J is 9, S is 18, B is, and you add them up, they add up to 41, right? And then if you just take this Bach part, right, you get 2 plus 1 plus 3 plus 8, and that's 14, which is 41 with the digits to it. Yeah, so interesting stuff, just nice stuff here and there, right? But this guy Smend, right, he wrote a book, he had this whole theory that Bach was almost obsessed with this natural order alphabet, and that it showed up way too often in his works for it to be a coincidence, right? But then there's another author, Tatlow, who seemed to make it her job to completely discredit Smend and all the work that he did to show that Bach used this natural order alphabet. And and it does appear in many other areas. Okay, and it just so happens that this slide is slide 14. I just noticed that. And then okay, so after we found these 11 NDH numbers, we wanted to show that there was infinitely many of them. We wanted to know that they weren't just cut off at 11, that we had plenty of others to go. So we ended up writing a proof for 2 to the n times 41 is an NDH number for all n. So you have an infinite amount of n, so you're going to have an infinite amount of 2 to the n times 41. Okay, and we did the same thing for 3 to the n times 41. So we have an infinite amount of these NDH numbers. And then we looked into primes, because primes are fun and we all like primes, and primes are the interesting numbers to look at. And again, if you look at it, a Fermat prime, this is what we're looking at. So a Fermat prime is a prime in the form of 2 to the second power to a k power, and then all of that plus 1. Right? And again, this is the difference of harmonics, right? Oh, not a difference, a sum, actually. But there's 1 is a harmonic number, 2 to the k is a harmonic number. And we only care about the cases where these are prime, right? And with that being said, there are only 5 known. It's believed that there may be an infinite amount, but we're not sure. But for these 5, we know that they're prime numbers. So when you plug in 0, you get 3. We know that's prime. You plug in 1, you get 5. That's prime. 17, prime. 257, a little bit harder to see that it's prime. And then 65,537, a little bit harder to see that it's prime. You have to work through it. But we did come up with a theorem, and this theorem was that any Fermat prime in this form with k greater than or equal to 3 is an NDH number. So as you notice, if you cut it off here at 3, right? This 3, that can be written as a difference of harmonic numbers, but this 4 cannot. And anything above 4, so greater than or equal to 3, can't be written as a difference of harmonic numbers, so it's an NDH number. Okay? So there's that. And then we get into the ABC conjecture. So this is the money. If all the math professors should know the ABC conjecture. It's a famous conjecture in number theory, not been proven. So the ABC conjecture states that if you have relatively prime numbers A, B, and C, and they satisfy the condition A plus B equals C, then C usually isn't much larger than the radical of A times B times C. So again, the radical of an integer is the product of its prime factors. So if we were to take the radical of 36, and it's going to look a little bit sketchy because as most people remember the radical as the square root, right? And it just so happens that this radical 36 ends up being 6. But it doesn't always match up that nicely. So we take 36, right? And then we break it up into its prime decomposition. So we have 2 to the second times 3 to the second. But we only focus on the bases, right? The prime bases. We kind of ignore the exponents, and then we just take that. And so we get 2 times 3, and that's equal to 6. And then we were able to join these, the ABC conjecture. We wanted to see if it was true on certain numbers. The original statement by Gersonity is the one where you say that for the only consecutive harmonic numbers above 4 are 8 and 9. It can also be reformatted into saying that the ABC conjecture is true on the set of harmonic numbers. So it's an alternative way of saying Gersonity's theorem. And then we also joined it with a finite set of NDH numbers. So the ABC conjecture is true on the harmonic numbers joined with a finite set of NDH numbers. And then proposition 7 is the ABC conjecture is true on the set of harmonic numbers joined with the set of Fermat primes. And this was our money, right? We expanded the set of numbers that are true on the ABC conjecture. Okay, and that's it.